Thank you, everyone. You can hear me okay? I'm thrilled to see this many people packed in here. This is fantastic. Right this very day in San Francisco, the first inaugural KubeCon is going on, where we're having our own little convention of sorts. And I'm here with you guys instead. It's going to be a lot of fun. So I do have 99 slides, so I'm going to try to race through them. At any point, if you have questions, please raise your hand, scream out, jump up and down, do something so I can see you. This is Kubernetes 201. Okay, if you missed Kubernetes 101, see me after class. Really, I'm going to race through a couple of the basics to move on to some of the more interesting, newer topics. If you feel like you're lost and you need a little bit of background, just ask a question. There will be a BOF later tonight, so if you have questions, I can come and do that too. I've also got some live demos, which I think are fun, because I haven't seen nearly enough of those today, so I'm hoping I can get to those. So, obligatory background. Google has been doing containers for a little while, about 12 years. Everything we do runs in containers. That's Gmail, search, web, ads, everything. We literally rerun billions of containers every week. Billions is plural. I don't actually have a current number, but last year it was over 2. So it's probably on the order of 3 this year. Everything about containers, and there's been a bunch of container talks, and they've been very well attended here. Guys at the door, you can please come in. There's some seats in here. They've been well attended. Everybody's interested in containers, but man, are they different. Quick show of hands. Who's actually running containers in production? Not just like fiddling around testing them, but in production. So it's like a third of you maybe, right? Now, how many people want to do it in production but aren't quite sure how to do it yet? Yeah, that's half of the room. So it requires new tooling. It requires a new way of thinking about the problem of administering applications and clusters. So this is what we're bringing you with Kubernetes. Kubernetes, sticking with the Docker nautical theme, is the guy who drives the boat, right? So it's also the root word of cybernetic, which is I just sort of fun. Kubernetes, from the beginning, I want to tell you, it is 100% open source. It is offered by Google, but it is not necessarily driven by Google. We have a huge community of contributors. 500 plus people contributed this year. On any given month, it's well over 70 people contributing. It is 100% open source. Everything we do is out in the open. So just a quick background. From 10,000 feet, all you really care about is, as a user, you talk to our Kubernetes master, which is this abstraction that exists within our cluster, and the master does work for you. Or more simply, you talk to an API, we talk to the container cluster. Now, containers, container clusters, it's a two-part story. The first part is setting things up. And this is where Kubernetes takes a lot of flack. It's a little bit difficult to set up. The networking is a little bit persnickety. You have to choose what cloud you're going to run in and set up your machines and manage these machines. These sound like familiar problems, right? Everybody here, this is a sysadmin-focused conference. People here are familiar with these sets of problems. This is not really the fun, sexy part of Kubernetes, but it is required. Now, if you're interested in Kubernetes, you haven't played with it, and you want to just try it out, for God's sakes, don't make this be your first experience, right? This is like running into a brick wall. We're working on it, but it's a little complicated. There are ways of getting Kubernetes up and running that don't require setting up a networking overlay, for example. The second part of this problem is the fun, sexy part. This is running applications and making things go faster, right? This being a sysadmin conference, I'm slanting today's talk towards some of the more admin-centric constructs that we've got. So first word around networking. So by default, Docker networking Docker's wonderful, right? It's wonderful simplicity, but with the simplicity comes a little bit of naivety, right? It pretends that the machine is the network and that's it. Up until very recently, and I'll talk about that in a minute. The idea is that containers on a local machine can talk to each other, but containers on different machines can't really talk to each other, except if you introduce network translation in between them. And specifically, the network translation comes in the form of port mapping, right? So you map a port on the host, and you talk back and forth, and you lose all sorts of network information, and it's really complicated to understand. The big issue is now, if you want to publish your application to another application, you have to tell it what port you've got on the host. And if you want to use port 80, but somebody else is using port 80, well, too bad, you're out of luck. And it gets really complicated. So from the very beginning of Kubernetes, we threw that idea out. We said it's not going to work. And so instead, we introduced this idea that containers are routable, that every container can talk to every other container on the network, and there's no port brokering, there's no mapping in between. This is a pretty fundamental piece of Kubernetes, and sometimes this is a complicated part to set up, even though it really is sort of the way things should work. And in fact, Docker now with 1.9 has introduced their overlay networking driver, which gives you exactly this, right? So thank you guys for making it much easier. So this is the basic model of networking. So when I talk about networking, if you're familiar with Docker, you have to forget what you know. Okay, this being Kubernetes 201, I'm not going to spend a lot of time talking about pods. Quick show of hands. Does anybody not know what a pod is? It's okay. Okay, real quick. Pod is a group of containers that we run together. It is our scheduling atom. It is a set usually of things that are tightly coupled, but you can think of it like a container or like a VM that has a set of processes that coordinate with each other. I'll talk more. There will be BOF later. If people want to see more background, I'm happy to talk more background there. Everything in our system has labels attached to them. Labels are arbitrary metadata that you can attach to the API objects through our API, and various constructs in our API then use those labels. When you think of it like select statements, right? I want to select all my pods where the label foo has the value bar. It's a very simple concept, but it gives us the ability to decouple all sorts of parts of our system and say that grouping is an artificial construct. There are no groups in Kubernetes, there are only selectors. Okay, so replication control. Kubernetes, you get there, you want to run your Docker application, but I need to scale it, or God, I don't want it to crash, right? If it crashes, I want it to restart, or if my machine dies, I need it to come back up on a different machine, because machines never die, right? But if they do, it's going to be at 3 o'clock in the morning on a Sunday. So replication control is our basic concept that says, I am asserting that I need n copies of this container running in my cluster, go make it so, right? We wanted to call make it so, but it wasn't, it's too cute. So it's just a real simple control loop. Are there enough running? If there's not, start more. Are there too many running? If there are, kill some. That's it. That's all it does. I have live demos of these things that I can do, but I'm going to focus on more new stuff. So services, there's 3 main constructs to Kubernetes. There's pods, replication control, and services. A service is just what you think it is. It's a bunch of pods that work together to offer something to other applications, right? Generally, you think of it as things like a load-balanced set, maybe a web server or something like this, an API. In Kubernetes, when you define a service, it's a capital S, it's in our API, what you get is a virtual IP address. That virtual IP address is a stable IP address. So all of the backends that are in your service, they can change, right? You can bring up or down containers, you can grow your set, you can shrink your set. It doesn't matter. That stable IP address is yours until you let go of it. What this lets us do then is define DNS. And everybody says, well, hold on, DNS just works anyway, right? To a first order, every DNS client in the world is broken because none of them respect TTL, right? Whatever application you wrote, if you do a DNS lookup, I bet $10 you don't respect TTL. And nobody collect on that, please. So we produce this concept of virtual IPs. So here's where I'm going to jump off into the what's new part of Kubernetes. So as of last week, we released Kubernetes, as of this week, we released Kubernetes version 1.1. I want to talk about some of the new features in 1.1. So one of the big things we did in Kubernetes 1.1 is we changed our virtual IP model from a user space proxy to a pure in-kernel proxy. The first version, we would bounce your processes out into user space. So we'll talk a little bit about the replacement. First, we would bounce your processes, We would bounce your processes to user space, copy some packets, move it on to the other client, to the other backend. And it was really simple, and it was good to implement, but it turns out to actually have a big performance hit, right? And it was a big scaling problem. And the Red Hat folks measured something like 40% of total throughput that they could get through this user space proxy. And it came at a huge cost of CPU because you had to copy the packets. And so it was great for a prototype, not so much for a real system. So here we are now with a real version. So the new version goes like this. We have our API server, and existing in our cluster somewhere, we have a node. On that node, we have our kube proxy, which is our agent for implementing virtual IP, and we have IP tables. The first thing that happens is the kube proxy sets up a watch on our API, and it says basically, anytime any services or endpoints change, call me back, right? And then it basically goes to sleep. Now, along comes a user who says, hey, I want to run some containers in my cluster. So he says kubectl run, which goes out and schedules a bunch of containers. Now he says those containers are running. I want to take them and I want to expose them as a service. So this set, and it will be a label selector, and I'll do a little demo of service in a minute. I want to run this set of containers as a service. Suddenly, the API server wakes up and says, hey, there's a new service, and it tells the kube proxy about it. So kube proxy goes out and configures IP tables, which produces a virtual IP. It's literally an IP tables matching rule that says any traffic that is destined for this IP on this port, trap it, right? Currently, though, it's going nowhere because there's no backends of this service because we only got an update on the services list. Now the API server comes along and has evaluated this label selector, and it said, hey, I've selected those 3 pods there. That's the little icon for pod. Get used to it. And it says there's new endpoints. Now the kube proxy says, OK, I know what to do with that. And it introduces a randomizer. And I thought that would work. And it's a perfect randomizer. And the randomizer then redirects to backends, right? So now we've got this virtual setup configured. Let's use it. So along comes a client application, and the client application says, well, I want to access this virtual IP address, right? Whether that's by name or whether it's by the IP address that we've given it, it knows somehow what to find. Generally, what you find is like, it's my MySQL service, right? So I use the name MySQL, and MySQL resolved to an IP address turned into this virtual IP. Traffic goes through the virtual IP into our randomizer, and then gets picked to one of the random backends. It never transits up into user space. And so our benchmarking now shows there's no CPU overhead to this, because it's all stuff that would have happened anyway. And as compared to raw IP to IP throughput, we're at over 96%. So there's almost no cost for introducing this. And the beauty here is that I can change that backend set without my clients worrying. So who wants a live demo? All right, let's see how the demo gods are doing today. So I'm running these demos. They're scripted demos because I can't type in front of an audience. But they are real, and they're running against my Google Compute Engine cluster right now. So I brought up this cluster about 2 weeks ago in preparation for this, and I've been sort of playing with it ever since. So let's first run setup. So there's a feature of Kubernetes called namespaces. And what namespaces do is they give you a private slice of the cluster, so you can use whatever names for whatever object you create without stepping on anybody else's toes. So we're going to create a namespace for the demo. And mostly we feed things in through YAML files, because YAML is a little bit more human-friendly than JSON. But JSON works just as well. So here's the YAML file. You can see that I have an object of type namespace, and it's named is demos. OK, now it's created. And I can prove it by getting it back. And you can see now it's 6 seconds old as opposed to the other ones, which are almost 2 weeks old. All right, so the first thing I'm going to do is use kubectl run, which is similar to Docker run, except it runs a replication controller and it takes a number of replicas. So I've gone off and I've created 5 replicas of this container, where all this container does is serve its own host name as an HTTP port, just so you can see that there are different containers running. Now I'm going to use kubectl expose, which takes the labels that I just applied and creates a service based on it. And it's going to receive traffic on port 80, and it's going to forward traffic to the backend on port 9376, just to prove to you that I can port map. So there's my service. You can see that I've got a bunch of backends that have been attached to the service. While we've been talking, all the nodes in the cluster have been updated, so they've set up their virtual IPs. It happened pretty much instantly. Now I'm going to SSH. Let's see if this works. I'm going to SSH into one of the nodes on my cluster. And I'm going to just curl that service IP. And what I should get is 5 different host names. Looks right. So I will now curl it a bunch of times, and we'll run it through unique, and we'll see just how the probability works. This is my dice roll here. Come on, D20, don't fail me. Okay, so it's not perfect, but it's pretty darn close. And when you start talking about large numbers, it gets even closer. What happened is what I just explained, right? It went through IP tables, it got randomized, and it picked a random backend. The client, meantime, had no idea. The client just said curl, right? So now for the real fun, I'm going to hit that service IP, and we're going to see the results of it, and I'm going to then change the constituency of that set on the fly, right? I'm going to scale it up and down. So it turns out that 5 was too many, and I'm just going to bring it down to 1, right? So you can see there on the left that now I'm only hitting my 1 backend, and it just picked 4 at random to kill. It turns out, actually, I made a mistake. I meant 2. So over the summer, we had an intern who thought this was sort of fun, and he wrote a diurnal controller, which is just a really simple program that took a list of timestamps and a set of targets, and it would then oscillate your replication count over the course of a day. So you could ramp up in the morning and ramp down in the evening. Right? It's just sort of a neat trick, and he did in the background. So now I'll bring it back up to 5. And you can see just sort of how quick things are happening. Right? The longest part of this whole process is pulling the image. Now, the image is already pulled because all the machines in my cluster have already got it, so this is why it's going pretty quick. And then we'll change it one more time. We'll bump it up to 10. And this works great. And if I felt daring, I'd bump it up to 1,000 and see what happens. But I only have 3 nodes in my cluster, so maybe not a great idea. So you can see there a very basic demo of services. Now, keep that in mind as we start building up newer, more fun ideas on it. So also new in Kubernetes 1.1 is we've introduced the concept of an L7 HTTP load balancer. It takes in client requests, and you can then map it based on URL paths or HTTP host names to different service backends. Our previous load balancer was only an L3, L4 balancer, TCP and UDP. Now we've got HTTP support. This is beta in Kube 1.1. All right, so I talked about namespaces. Now I want to talk about it more because honestly, namespaces is one of my favorite features of the system. And here's the fun part about being open source. We would never have implemented this feature. It was something that the Red Hat guys came to us and said, we really need this, and can we build something like this in Kubernetes? And we said, I don't know that it's really that useful, really. We don't do it inside Google. I'm not sure that you really need it. And they argued and they argued and they justified why they needed it. We let them build it. It's so cool. Because when I'm done with this demo, I'm going to run one command. I'm going to blow away everything I just did by deleting the namespace. So it's really a matter of giving people private subclusters, right? It doesn't tie to any one node. You're not subject to being scheduled on only a slice of the cluster, but you can't see anybody else and they can't see you, which means you can choose names for your services that are short and descriptive, like MySQL or database, right? And you don't have to worry about anybody else. It means that all of the things that you create and do, they're yours, right? I'll talk about services later if I have time, secrets. And you can create secrets, and they're only published to people in your namespace. And you can then start to build a multi-tenant model here where you build, your marketing department and your engineering department have different namespaces, and they can run the same stuff but not see each other. Or, more fun, you can have your dev namespace and your test namespace and your production namespace, and you can have all of your setup run exactly the same, but you can actually change the implementation of what it means to be the database, right? In your test cluster, it might be a lone MySQL, and in your production cluster, it might be Oracle, right, or whatever. Pick your interchangeable parts, but you can change things out. It's this awesome idea of implementations and interfaces, right? This thing that we all get as software engineers. We're now bringing it up a level of the cluster. So this is one of my favorite features of Kubernetes, and it's just this great example of why open source is so powerful. All right, so people here, how many people are sysadmins? Yeah. So ever run a job on a machine and have somebody else complain to you that their job suddenly got slow, right? I brought up my database on a machine, and some user logged in and ran GDB on something, and I got killed, right? It's never happened to me. Resource isolation is a huge deal. For Google, this is everything. In fact, at Google, what we call containers, we don't even use namespaces because we don't really care if you can PS and see my processes. What we care about is that no matter what you do, you can't hurt my process. You can't cause degradation in my quality of service, right? It's so important that every summer when the interns start and they find a hole in the system, because they always do, right? They come in and they say, I'm going to run a MapReduce. I wonder how many zeros I can put at the end of my replica count. Let's try 100,000 and see what happens. And that's a P0 bug, and we're ready for it every May and June. Some intern comes in and causes a problem, and we find it. What we do with this is we define quality of service bands, right? When we talk about quality of service, what we really want to talk about is SLOs, right? Service level objectives. What am I promising to give you, and not what controls am I giving you, right? I don't want you to drive and tell me the details of what you want to do. I want you to tell me what you need and let me decide how to offer it to you. So the upside here is you can build your applications based on these SLOs, and your users can. And then when you violate the SLOs, you have escalation policies. You can set off a pager, you can send an email, you can decide what to do when these things are failing. The flip side of giving people strong isolation is you have to deal with what happens when it fails, right? Either you end up stranding resources, like some user wanted all the CPU but not all the memory. Now you have wasted memory. Or you have users who are confused. They just don't know how much to pick. So they stick their finger in the wind and they say, I don't know, 4 gigs sounds good to me. And then it turns out they're wrong and then their apps crash and they get pissed off, right? But there was free memory on the system. Why couldn't I use it? Because you chose 4 gigs. So in Kubernetes, we've got this concept of requests and limits. And this is how you book resources in Kubernetes. And we've got 3 bands of quality of service. So request is guaranteed. If you ask for 4 gigs of memory, I'm going to give you 4 gigs of memory. I'm going to put you on a machine that I believe has 4 gigs of memory for you. And that's what you're guaranteed to get. And I won't overcommit. If you ask for 4 gigs, but you say, but I'd like to use 6 if it's available, right? That's your limit. So the quality of service bands that we define are this. If you set your request and your limit to the same level, you are considered well-behaved and you get guaranteed resources. And if something goes wrong with your process, we'll know about it. If you set your limit higher than your request, you're what's called burstable, but you're still well-behaved because you're telling us what you want, right? But now if something goes really wrong on the system, we're going to do something bad to the burstable processes before we do something bad to the guaranteed processes. And then at the bottom of this is best effort. If you don't specify what you want, you basically get no protections, right? What this means is, let's consider out of memory, right? Out of memory is sort of the bane of every developer's life, right? I wrote my application, and the system went out of memory, and I don't know what happened, right? And Linux has a general policy of shoot into the crowd, see what happens. Maybe it'll get better. So we use these quality of service bands to do things like set the score levels so that when Linux shoots into the crowd, it's going to shoot into the low priority crowd before it shoots into the medium priority crowd, before it shoots into the high priority crowd, right? It's not exactly a guarantee, but it's a pretty good way of making sure that your important applications get protected. And it's a pretty good carrot for you to write your applications and benchmark your applications so that you know what resources you're actually using. So now let's talk about enforcement. So it's no good to talk about these things without quota, right? So Kubernetes has quota. Quota is something that you attach to a namespace, and it lets you manage resources in aggregate. So for the namespace, you're allowed to use 4 gigabytes of memory. And if you want to use more than 4 gigabytes of memory, it's going to fail. It's not going to schedule. I'll show you in demo in a minute. It's sort of like disk quota, if you've set up disk quota before. By design, it's meant to be familiar here. And it applies to the different resource dimensions. Right now, we do CPU and memory, but over time, we'll accumulate more types of resources that you'll be able to do quota on. And what's interesting is once you install a quota, you can no longer create best effort pods, right? Because you have a quota, and I have to do accounting, and 0 is not a number. So to go with quota, we have its best friend called limit range. What limit range does is it lets you set brackets on what people are allowed to request. So I can set a lower bound, I can set an upper bound, and I can set a default. Let's do the demo. So first off, I'll show you there is no Quota installed in my demo's namespace. So I'm going to go ahead and install some Quota. I'm setting a hard limit of 4 CPUs and 4 gigabytes of memory. So I went ahead and created it. Now let's look at what I just did, and it'll show you. There's nothing used. It's got no stats on it. So I'm going to try to create a pod that is too big. You can see here that I'm trying to use 4.1 CPUs and 4.1 gigabytes of memory, right? Both in violation of what we said before. And the error says, E go away, right? And it gave me back both errors so that I know as user what to do. So I'm going to go ahead and install, you can see now that the Quota hasn't actually changed, right? You can see that it's been refreshed finally, but there's no usage. So now I'm going to create a pod with no request, right? Which I previously said was not allowed. And this should also fail. Bang. Okay. So let's get around that by installing, it's going to show that again. There are no limits installed. So I'm going to install a default of 100 millicores and 256 megabytes of memory. So now if I schedule a job that doesn't ask for any resources, this is what it's going to get. So you can see now that my request default is there. And we'll, again, try to create that pod. And now it's succeeded. And you can see that, in fact, it's tracking my Quota, right? So now you can take your cluster and you can give your development team a bounds, right? And make sure that they don't run away with the cluster. And you can give your production team good guarantees on what sort of resources they're going to get, right? Are there any questions so far? Sorry?
The 100M for CPU.
What is the 100M for CPU? M is milli. 100 millicores, so a tenth of a CPU. Okay. We measure CPU in the native unit is millicores, and so it just makes more sense that way. Floating point is hard. So now let's talk about networking. So I mentioned networking earlier. This is the most complicated topic in container space, I think. Every network out there is a special snowflake. It is different from every other network out there. It depends on what equipment your CIO bought and what equipment has lasted this long and who gave you a freebie and how you glued all these things together and how your sysadmin from 10 years ago set things up. Every network is different. And when it comes to things like Kubernetes, where we sort of pretend IP addresses are free, it gets sort of complicated. So in Cube 1.0, we introduced a basic concept of plugins. In Cube 1.1, we've strengthened that a little bit more. The idea here is, as an administrator, you can configure your local installation with whatever networking you really need to set it up, right? This is something that popped out really early in Docker through a process called pipework, which I know Jerome's over there. And it emerged as a very early problem of, but my network is different, right? I need to use Mac VLAN. I need to use, pick your favorite network technology. We don't want to be in the business of having a built-in driver for every possible framework out there, so we're just going to give you a plugin, right? And the plugin interface is very simple to code to, and it's just exec and fire and forget. You set up your network the way you want to set it up. Let's talk about cluster scaling. So this is the fun of software-defined infrastructure, right? For all of you who run hardware infrastructure, I'm sorry. My cluster, it's burning down. I need more machines. What do I do? We've now got cluster AutoScaling built into Kubernetes 1.1. So when your cluster reaches certain thresholds, you can automatically grow the cluster. This is very early. It works on GCE right now. We need to get other implementations on other platforms. But the main idea is if, for example, my memory utilization on average across all the machines is larger than 80%, I'm going to just bring up more machines of the same template. I'm just going to start stamping out new machines. The machine comes up, registers itself with the API server, and the API server will start scheduling to it. Right? It will not do, at that moment, a rebalance. The goal here is not to be balanced. The goal is to have enough. Right? We'll get more robust as time goes on with this. So a question that we get a lot in Kubernetes is, I have 100 nodes, and I need to run a process on every single node. Or I want to run a process on all the nodes that happen to have SSDs attached to them. How do I do this? Right? And up until Kube 1.1, we did not have a good answer. Right? The answer was, well, you can maybe do something with host ports and sort of trick the system into running at most one per machine, but that doesn't necessarily guarantee you'll get all the same machines that you want. So we've introduced this concept called a daemon set. And a daemon set basically says, take a label selector and select nodes that match this selector and go and run this pod on the nodes that match that selector at most one time. Right? It's a pretty simple, straightforward idea, but it took us a while to sort of get the factoring the way we wanted it. Now that we have it, though, we're going to use it for everything. So let's do another demo. This is one of my favorite demos. All right, so you can see here, I'm going to use a Go template. Please pardon the noise. You can see here all my nodes and the labels that are applied to those nodes. And in this case, you can see that none of these nodes have a color label. So I'm going to use the color label. So first, I'm going to set up a service. And this service, you can see here, is selecting for demo equals daemons. Okay? Now, I didn't run any pods that have demo equals daemons. So right now, this selector is, the service is going nowhere. Right? It's a virtual IP that goes nowhere. So now I'm going to run a daemon set. And the daemon set has my pod template in here. And the pod template says it has to run on nodes that are colored red. And it's going to offer the label demo daemons, right? So this pod would satisfy my service if only I could get the pod to run. But the pod can't run because none of my nodes are red. So we'll see. The last time I ran this demo, it failed. Okay, so you can see here that I've got 0, 0, 0. Nothing is running. All right. So here I'm going to hit that service. And every connection I make is just going to time out because there's no backends. That IP address just doesn't exist. Okay, so now on the right, I'm going to go through one by one, and I'm going to color each node. And you should see that service pop to life as each one happens. Here we go. Bam. Just like that. And in a few seconds, it'll do the next one. In a few seconds, it'll do the next one. And so you can see through this how you could do something like, say I want to run a storage server, right? I want to run Ceph or Gluster, and I want to put it on all of my nodes that have a lot of storage, right? You could label your nodes as has big disks, and then run your application, right? This gives you a lot of power to configure your system sort of in a distributed way, right? If you think of it sort of like a distributed init, kind of, in a way, it lets you run processes across your cluster, set up your nodes the way you need them to be set up, all containerized because containers are fantastic and that's the power. And it lets you use them through all of our same API tooling, through the UIs that are here. I'm not going to show off the UIs, but there are UIs for Kubernetes that will let you manage and look at and visualize all of these things all together, which is a big step forward. Inside Google, it took us years to come around to the idea that the stuff that we ran as like services on the node should themselves be reported to and managed by the cluster system, right? It's this sort of self-hosting concept. Once you can see things, you can manage them. So you can see now I've colored all my nodes and I've got them all running. Questions so far? Yeah.
So is it now possible to run the kubelet inside a container?
Is it possible to run the kubelet inside a container? The answer is like 90% yes, so no. There are, it's getting better. There are a few things that we're continuing to chip away at running the kubelet inside a container. The biggest problem right now is kubelet will mount volumes for containers, but it will mount them inside its own namespace, which isn't propagated outside of the kubelet, so therefore the other containers can't see them. And I can't tell you how many bugs are actually open on this right now, and it just doesn't work, guys. I understand that the feature for mount propagation is in Docker 1.10, and so any month now, no, they just did 1.9. Give them a minute to breathe. Any minute now, we'll have a new Docker that will support this properly, and then I think we'll be at like 99%. Right? I leave 1% because I don't know. Right? But we're really working towards getting kubelet itself running in a container so that the turtle at the bottom of our stack is Docker. Right? Sorry, daemon sets in Kubernetes 1.1 is considered alpha, which means we might radically change the API. We probably won't, but we reserve the right. All right, let's talk about storage, because man, storage is hard, right? So how do you do storage in a containerized world? The general answer is badly, right? Containers are fantastic for stateless applications. They're fantastic if you can say, don't store your files, don't write anything locally, use the network, right? That's great, but again, to lean on the turtle analogy, there's got to be a turtle somewhere that is standing on something that isn't another turtle. And so for us, we have this idea of persistent volumes. So we use volumes the same way that Docker uses volumes. Persistent volume gives us an abstraction at the cluster level that lets users request and release storage that has lifetime that's bounded larger than their own application. So the idea here is, as an administrator, you know that you are running in Google Compute Engine or in Amazon or some other installation, right? I don't want your users, I don't want Kubernetes developers knowing that they're running in Amazon, because I don't want them to couple to the Amazon platform. Big deal in Kubernetes is coupling. So, but I don't mind you, the admins, knowing, because you're going to know, right? So you come out and you say, well, I'm going to create some persistent volumes in the Kubernetes API that represent EBS volumes in Amazon, or PDs in GCE, or iSCSI mounts in your own local installation, or NFS shares, or something else, right? We have a dozen different ways to describe volumes. You as the administrator can describe them in an abstract way, right? Their capacity is 100 gigs, and they're mountable in read-write only, or sorry, read-write once, or multi-writer mode. Like NFS can be multi-writer, block devices can't, right? Then as a user, I can ask for storage. I can say, hey, I need 100 gigabytes. And the system will then schedule, common concept, your claim for storage onto a back-end volume, right? And then I can give the user that volume without the user ever knowing anything about what kind of volume they took, right? So let's look at it a little bit more graphically. So as a cluster administrator, you create these persistent volumes. And these persistent volumes are backed by something real, right? For now. In Kube 1.2, they will be dynamic. But in Kube 1.1, they're still real things. So you can go out and provision three EBS volumes, and you create 3 PDs to map to those EBS volumes. Now a user comes along and schedules a persistent volume claim. And the claim says something like literally 100 gigs, like capacity 100 gigs. The persistent volume binder walks through all of the persistent volumes and does a best fit and says, okay, this is the volume that's least expensive that will fit it. Now as a user, I can schedule a pod which references that claim, which means that whatever that back-end volume is going to get mounted into my pod automatically, right? So as a user, I can put my MySQL files there, and I can write them to this persistent volume, and I can know that they're safe. They're stored on my EBS volume, right? Now, something happens, and the database, I decide I don't want it anymore, right? But I want to keep the data, because I want to do some post-mortem or something on it, right? So I can schedule another pod that references that same claim, and now I can get my data back, and I can do things with it. So imagine that you want to build a video transcoding pipeline, right, where you want to run a sequence of pods, and you want to hand off the data in between them. The first chunk gets your raw DVD ISO images, and the second chunk produces MKV files, and the third chunk produces optimized whatever, extracts all the subtitles. And you can build this pipeline of independent processing steps while storing all the data in this persistent volume. And then at the end of your process, you can delete the claim, and the volume goes away, and we recycle it, and we give it to somebody else, right? It's pretty simple in concept, but there's a lot of moving parts. And so this is something that we've been working on in Kubernetes 1.1, and we're continuing to work on in Kubernetes 1.2, is the idea now that you'll be able to do this dynamically so that you don't actually have to pre-provision these things. As an admin, you should be able to set a budget. Say, I'm allowed to have 10 EBS volumes of no larger than 100 terabytes, and go create them when you need them, because these things cost real money. Everybody, who here runs stuff in AWS or GCE? All right, who's got a budget of more than 10 grand a month? Yeah, right. Just what you need is more volume sitting around charging you, 15 cents a gig, right? So this is the persistent volumes construct. Secrets. So we're starting to move back into user application territory here. As somebody who builds applications, you have these applications and they communicate with each other, but sometimes they need things like a password, right? Great idea, putting a password on your database. So how do you get the password into the application that wants to use it, right? Do you build it into the container image? No. The 12-factor rules say you put it in the environment, right? Where people typically think environment means environment variables, and that's how you do it. And that's a great way to do it if that's what you have. I think what we have is a nicer API here. You can go to our API, and you can create a secret object. And in that secret object, you're going to put your password. And you can then reference that secret object from a pod the same way we referenced a claim from the pod. And it will create you a virtual volume, and it will pull that secret down, and it will store the secret for you. That volume is in tempfs, so you don't have to worry about it ever hitting spinning media, or magnetic media, rather. And then as an application, you can use it. It gives you this great decoupling, here I am again, of your injected secrets and your runtime applications. So they're late bound. You can change the passwords. You can have different passwords in different environments, right? Something I'm not talking about today is service accounts, which also come with namespaces. But you can set up different service accounts to have different levels of password to the different backends. So let's do another demo. So you can see here the YAML for my secret object. And I store the contents actually at base 64 because they might be binary, right? So we'll send that up to our server. We have a couple different types of secrets. We have Docker pull secrets, so you can actually store credentials for Docker registries and use that to pull images down for your applications. So I've gone ahead and created a password. Now I'm going to use a pod, and all this pod does is go to sleep. It does nothing useful. But it mounts my password on a volume called /data, and the volume mount is a secret, and it's going to reference the secret that I just created. And I'm doing this so that I can surreptitiously show you another feature. Yeah. Oh man, I'm running out of time. All right, this will be my last demo. So I've gone ahead and created that pod. And you can see it running. Now I'm going to exec into that pod. So it's running off my cluster somewhere, and I'm going to go sh into it. And now that I'm here, data. So you can see my username got unpacked. And oops. This is why I pre-script. And my password's unpacked too. So now my application, maybe that was my SSH key, right? My application can now use my SSH keys to do what it needs to do without actually having built those things into my image. This gives me the ability to version, deprecate my keys, and I can have my application, I can rev the application without worrying that the keys are propagating. All right. I'm told that I'm running out of time, so I'm going to jump through this. Did I mention I had 99 slides? So I was working this up, finishing these off last night, and I kept having to make the font smaller and smaller to pack all the things that I didn't talk about today into this. And this is certainly not all. I'm sure that I forgot important ones. But the left-hand column is a bunch of stuff that's in Kube 1.1, and the right-hand column is a bunch of stuff that's coming and probably will be shooting for Kube 1.2, right? Wait till people take pictures. Now's your chance. Sorry, I ruined it.
In fairness, the next speaker, if you're going to ask a question, we're going to have time for maybe one or two.
Yeah.
If you're going to ask a question, get up to the microphone.
Yeah, if anybody wants to ask questions, now's the time. Otherwise, I'll be out afterwards, and I'll be happy to take questions or talk out in the hallway. So here's the quick status. We did just launch our v1.1. We're shooting for about a 4-month cadence, so we hope to have a 1.2 in early next year. We've got a bunch of platforms that are building on top of us and distros that are bundling with us. Big goal of Kubernetes, the question people ask is why? Why would you do this? We want to shake things up. We really believe that the way things have landed in the VM space isn't great for people, and that people are itching for something that's simpler to use. And if we just shake the snow globe, that we think more of the snow will land on our side when people are using containers. Reminder, Kubernetes is open community. Send us your patches. I will send you t-shirts. If you fix our bugs or fix our docs, I will love you forever, especially our docs. Any questions, guys?
I have one question. You said that the IPs are routable. Is that the same IP that's on the, or is it a same LAN that's on the host, or is it an overlay network on top of it?
So the question is that IPs are routable. Is it the same LAN as the host, or is it an overlay? It can be either. We have a lot of installations that use overlays like Flannel or OVS to set up VXLANs where the pods exist on a plane higher than the nodes. We also have installations like Amazon and GCE where I can actually program the fabric directly and set up a bunch of static routes. So like on GCE, I allocate a /24 network to each node, and then I use that to configure my Docker bridge and set up the static routing in the fabric so that anybody who's accessing those subnets will then get routed to the appropriate nodes. Right? So I don't need the overlay if I don't need the overlay. Other questions? All right, we will have a BOF tonight, so if people want to get down and dirty with it, I'm happy to do more demos, dig into code, talk about features, ideas, whatever. I also would like to hear from people about what you're doing with it or what you want from it in order to do something with it. I want it to be really bidirectional, so thank you guys for your time.